Alrighty, so today we're going to be going just a little bit over this thing. This doesn't really have a title, but it's an implementation of Hohmann transfers in 2 dimensions. If you don't know what Hohmann transfers are, check out the sister video that came out with this. It goes a little bit more into depth, or is I guess a little bit more of a concise explanation of what Hohmann transfers are and how they work. This program, what it allows you to do is it allows you to mark wherever, excuse me, you have this little satellite here in a very close orbit around a central body, which we'll pretend is Earth. It has the physics of Earth, as we'll see later. And at any point, we can mark the current radius or the current orbit of this object, and then change our target orbit, and then this little green blip will automatically conduct a Hohmann transfer maneuver from wherever it started to wherever it ended, and whenever it gets there, as we'll see, it will automatically circularize and fill the target orbit. And it has a couple extra features like trails and getting the mark to work. This kind of thing really only works in this manner, utilizing approximations. So in this case, it's another Euler approximation, like my last program that I put on here many moons ago. So anyway, we'll go ahead and take a look at how this works, but we can also, mark this orbit and tell it to go into a closer orbit, and it'll do that too. Anyway, and we can turn the markers off. You might notice there's a little bit of lag. That's because this is running on a very low-powered laptop. So this is all implemented in Python, as hopefully you could tell from the video title. And utilizing tkinter, which is a prepackaged GUI functionality that comes with Python. So if you want to run this program, and I do intend to put the code on Github, check the comments for that. If you want to run this, we'll check the dependencies here. The only thing you actually need to download in addition to Python is NumPy. There will be links to that in the comments as well, hopefully, if I remember to do that. Some obligatory questions. This is in Python because I know how to use Python. I'm using tkinter because I already know how to use tkinter, and I spend most of my time without access to internet. So I would implement this in Kiwi, which I'm given to understand is a lot better, except that I don't know how to use Kiwi, and I don't have regular enough internet access to have 26 pages, Google tabs open, telling me how to use it. That's the process. Why is this written in such an amateurish fashion, you may be wondering, and that is because I know more about physics than I do about programming, and I know more about history than I do about physics, and I only learned how to program at all in the spring of 2020, that is this year, thanks to Code Academy. So if you don't know how to use Python, maybe check that out. There's no sponsorship here. I'm nobody. So anyway, let's go ahead and get into it. So as you see here, we've imported some dependencies. In this case, we've imported time.sleep. This is useful for frame rate functions. We don't really use it for very much. We have from tkinter import all. That's everything that you see here. How the controls work, how the interface works. Literally everything that comes from here is from that tkinter module. We'll go ahead and close this to save on frame rate. So anyway, being a tkinter, oh, and we've also imported NumPy. If you don't know how to use NumPy, there are loads of videos on NumPy. It's pretty great. It lets you do direct vector mathematics if you're a math person. And one final thing before we move on, the point of me doing this is because if I had better hardware, I would be utilizing these principles to make video games that uh, have actual physics behind them. It would be nice to see something with real space physics, actual space physics other than Kerbal Space Program and Children of a Dead Earth, maybe an RTS, who knows. But I find there's a lot of potential there. It just seems that programmers are scared of things that involve calculus a lot of the time, and it's really not that scary if you're willing to let the machine do the work for you. Um, so anyway, we have our root node, which is establishing tkinter's presence here. We have a res x and a res y parameter separated by a semicolon here. These determine the actual uh, size of this window. So this is 1000 pixels by 700 pixels on my machine. You can set that to any parameter you want. You can even set it to be adaptive. You can have Python read the screen size of whatever machine it's running on and set it for that. I have it set for this because I am lazy, which will be my answer for a lot of things. And then I've went ahead, in order to find the center of this window, because of how the coordinate system works, wherein 0, 0 is the top left corner, and that res x, res y value is this bottom right corner. In order to find this center point, we need to take those two values, and divide them in half, and that tells us what pixel is in the exact middle. And so we've implemented that as a numpy array, which is just res x over 2, comma, res y over 2. You want to set it to a float, just because if you don't, there will often be problems. And then we've declared our canvas here. The background color is black. The height of the canvas is that y resolution, and the width is that res x. Then after the semicolon, we're going to go ahead and pack the canvas so that it exists inside of our root window. After that, we're going to declare some constants utilizing a dictionary. Why did I use a dictionary? I don't know. I kind of just felt like it. I don't know what the rules are. I'm sure I'm gonna. If anybody who watches this who's a real programmer is gonna have a whole lot of issues, that's okay. If you have issues, please rework this and make it much better, and then develop something super badass out of it. That would be awesome. These constants that we have declared here, we have a dt value. This tells us essentially how fast time passes. We have g, which is Newton's constant, or Newton's gravitational constant, which we need in order to do this math from the Hohmann transfer video, which if you haven't seen that, again, highly recommend it. We've declared that a kilometer is equal to 1,000. Your base unit doesn't really matter, but it's handy. And then we have T minus here. I don't know, I just gave it a random name, but that's going to be the amount of time that has elapsed since the beginning of the universe, according to the simulation. We are also going to, for the sake of some physics later on, going to be multiplying Newton's constant by dt. That is because Newton's constant is measured in kilograms or kilograms and meters and second. It scales with all of those. So if we're saying that 10 seconds pass at a time, we also have to multiply Newton's constant by 10, or big G by 10, in order to get the correct value for our math later on. We're also going to declare a scale factor, which is just 100 kilometers as defined earlier, so 100,000. This is what enables us to convert uh, Cartesian XY distances. Um, so if you have the center of the screen here and you have something that has, x 250 million kilometers and y 180 million kilometers, you need to divide it by something in order to have it all fit on the screen. That is your scale factor, SF, as declared here. We're also going to define the Earth according to its mass, which is 5.9 times 10 to the 24 kilograms, and its radius, which is approximately 6,371 kilometers. We're also going to declare a list called SatList. This is vestigial. I thought at one point I might have multiple satellites that you could control instead of just one, but didn't really do that. Oh well. But so this little green dot exists within that list declared there, uh, and everything kind of operates or loops based off of that. So after having built the list, we are going to create a class called satellite. We're going to give it some init parameters, so self, xy, which is just its coordinates. We have vxy, which is how fast it's going in either of those dimensions. And then we have a target altitude. And from those, we're going to create a parameter called state, which is a NumPy array consisting of both the xy value that we gave it and also its velocity. We're putting them both here because it's just a little bit more efficient on account of how NumPy arrays work, because these two values are going to be altering each other somewhat. And we're going to go ahead and declare its data type as a float again. We're going to declare its CAlt, or current altitude, which is a hypotenuse, rather the distance between it and that center that we talked about, the center of the Earth, which is just its x value here and its y value here. We're using NumPy declarations, so you have to set its first array, comma, or first array position, comma, second array position. And we're going to be utilizing that to have NumPy find the hypotenuse between those two values. And then its target altitude is that declared value from before. We have self.phase, which is what part of the maneuver the satellite is going to be in at any point that it takes this Hohmann transfer. It's a little bit more of a formality for a decision-making process, as we'll see later on. And then self.trail is a list of points so that we can do this little white line. Gosh, this is slow. We can do this little white line trail here that our object leaves behind it. So now, having declared all of these parameters, we can get into functions. First of all, we have gravity, which operates off of the current altitude, and as long as the current altitude is greater than the radius of Earth, it will find a force as defined by Newton's law of universal gravitation, which is big G times the Earth mass altogether, divided by that radius squared. Here the radius is the object's current altitude. From that, we're going to find a parameter called r hat, which is just the object's position divided by its altitude. That gives you a basis vector from which you can then apply your transformation. So you find the direction that the object needs to go, and then you multiply that direction vector by the force, and that tells you how far the object goes. Um, and so we're just going to apply that to change our velocity. This function is the subject of another video I've done before that I'll probably cover many, many, many times in the future. But this is just how we calculate gravity at any given point in space between two objects. Following that, we're going to actually be getting into our Hohmann transfer maneuvers. So we need to declare a value of mu. Before moving on, you might see that the parking maneuver and the transfer maneuver are basically copy-pasted. Yes, I am aware of this. I am sorry, it is not as pretty as it could be. So this mu value is going to be constant g, Newton's gravity constant, times, or in this case now we're having to divide it by our delta time, our dt value, how many seconds pass. Because this vis viva equation that everything operates on, mu does not incorporate this passage of time function. This is the only part of this where dt has to be taken out of the equation. So we get our velocity. This just tells us our raw speed, which is the hypotenuse between our Vx and Vy values. And these next two steps rotate that basis vector 90 degrees so that now instead of working with the so where r hat is pointed directly, r hat is the force that points directly at the planet. Now we need to rotate that 90 degrees so that we can find our tangential velocity at any given point. This enables us to find our tangential velocity here, for example, or at any other point in the orbit, really, or in space. Excuse me, I'm trailing off a little bit. So having found that normalized value, we then apply the vis viva equation, and then we just kind of set the velocity to that value. In real life, you would have to do math to apply to figure out if you were speeding up or slowing down. But in a programmatic setting, that is just one extra step between directly altering the value. So if you know that you need to go 3,500 miles per hour and you're currently going 4,000 miles per hour, you could subtract 500, or you could just say that you're going 3,500 miles per hour, and that seemed more reasonable to me. So that's how that works. And then following that, we're going to be setting our satellite's phase to parking. That's just so that you know that it's supposed to be remaining stationary at a particular orbit. The transfer is going to work exactly the same way, except that we need to find this little value here, which is the semi-major axis of your transfer orbit. That's this A value here, this little A line. And then you use that semi-major axis, which is just the radius of where you started and the radius of where you ended, divided by 2. You use that semi-major axis to figure out how fast you need to be going at your endpoint. You do the exact same thing there, and you set your velocity as that value. And then while it is transferring between the two circular orbits, we will set its phase to be transfer. Now we're going to be we're going to define a decision tree, essentially. If the current altitude integer division by 100,000 does not equal the target altitude divided by 100,000, integer divided by 100,000. And then if the phase is not equal to transferring, that is saying if you're not where you want to be and you're not transferring, transfer. However, if you are where you want to be and you're not parking, park. Pretty simple. And then we put it all together in the satellite loop where we tell it, well, whenever we run the satellite loop, we're going to alter our course because of gravity. Then we're going to check our altitude, right? Our altitude check is going to either make a maneuver or not make a maneuver. And then we are going to change our position according to our velocity. And the way we do that is we just add our velocity value to our position value, and we multiply that. We multiply our velocity by dt so that 10 seconds is equal to 10 seconds instead of 1 second. And then we add that to our current position. Now we are going to create an object based on this satellite class. This object is called test. So test equals satellite with a y position of 7,000 kilometers with a starting velocity of 0 and a target altitude of 7,000 kilometers. So that its target altitude and its current altitude are the same, so it will start off stationary. So as soon as it exists, it will run that altitude check and then circularize itself automatically, so that you don't have to define an initial velocity unless you really want to, but there's not a point. And then we're going to add that test object to that sat list. Again, sat list is purely vestigial. You can do everything without it if you wish. Now we're going to define our rendering functions, and don't worry, we're more than halfway there. This is almost done. We're going to define our rendering functions, where we're going to tell the tkinter canvas to delete everything. We're going to find the position where the Earth is supposed to be and draw a circle where that is, as defined by the central position that res x, res y over 2 plus the Earth's radius divided by the scale factor. And that will give us a circle on this window. On this window, it'll give us a circle with the correct radius and plop it down in the center. So that's how we create the Earth in those two lines. And then for every object in the sat list, we're going to find the object's position in the new scale, where we just take the object's position, divide the coordinates by the scale factor, and then we're going to add res x over 2 and res y over 2. Now, don't worry about this. This is the trails, but essentially, whenever we count down the seconds, if every 20 seconds it is going to add its position to that trail list we defined up here. So it's going to add its position to this list every 20 in-game, in-simulation seconds. If that list is more than 1,000 entries long, it will delete the first 2 entries, which correspond to a single XY coordinate, which means that it will maintain a length of 500 points, because that 1,000 is 1x and 1y, so over 2, 500. Um, and having done that, we're going to define the object's size. In this case, it's 3 pixels in each direction. We're going to go ahead and bump that up to 5 because why not, I guess. I felt like it. And having defined the actual icon that creates the little square here, which is that x1, x2, y1, y2, corresponds to this little square right here. Now we need to create that green circle representing its target altitude. This green circle. Oh my gosh. This little laptop doesn't particularly enjoy recording. This green circle going around the planet that we can move. If that list is greater, it has at least one set of coordinates in it, and a separate little doodad that says that it's okay to draw that red circle and the trail are on, then it will draw the trail. And now we are going to draw the little square. We are going to create some text in the window. Text in tkinter, you give it an X position and a Y position. You tell it which corner to attach to. You tell it what color to be, and you tell it what it should say. But so this tells you your current altitude and your target altitude and whether or not the satellite is parking. And then this one tells you how fast the object is going in kilometers per second. If that little doodad is on, then it will go ahead and create a circle indicating that, it'll go ahead and create a circle indicating the object's current position. You can see here that we changed the object size, and so now the square here is a little bit fatter. But this trail consists at any point of up to 500 points. Once we reach 500 points, it'll start cutting off pieces. But we're not going to wait for that to happen. And then having drawn everything, we're going to update the canvas. And then now we're going to do the main loop, G loop, game loop, whatever you want to call it, which says that while the number of seconds that have passed is less than the number of seconds you input whenever you utilize the loop, it's going to wait for 1.5 milliseconds, so just because it's better for keeping consistent frame rates. We're going to add dt to the number of seconds that have passed to tell you how many seconds have passed. And then for every object in that satellite list that we declared that only has the object test in it, we're going to go ahead and run its own personal sat loop. And then we're going to run the render loop. Now we need to declare some controls. So I'll tell you what they do here real quick. If this thing will load up here in just a second. So your target altitude here is controlled by the mouse wheel. So I scroll up and my target altitude increases. I scroll down and it decreases. I left click whenever I want to activate the trails and mark my current altitude, and I right click whenever I want to hide those. That is all of the controls. So whenever I mouse wheel up, which is declared by button 4, which just means mouse wheel up, we're going to increase our test alt by the scale factor times 5, which is actually just 5 pixels. And then it converts all of that back into its new target altitude. And whenever I scroll down, it does the same thing, but in reverse. It subtracts the target altitude by the scale factor times 5. I don't remember what this does. but I suspect that it is an oversight because I'm absent-minded. And this little doodad is what allows you to turn on the trailing features on or off. This declares that whenever you click the mouse button, it marks the current altitude. Oh, that's right, what it does. It marks the current altitude of wherever the satellite is, and the object in this gets converted into those red circles that tell you where it was whenever you clicked. This does the same thing in opposite, and then we just declare our main loop to run for 100,000 seconds, and then we have to declare our tkinter main loop. And that's this whole program, 127 lines. You have automatic Hohmann transfers and a solution to the two-body problem with some relatively simple to implement graphics. I put all this together in like maybe 2 days, probably like 4 hours of actual effort. So anyway, I hope that wasn't too scary. If you have any questions, please leave them in the comments. I don't quite know what I'm doing, but I would like to see more programmers get into, or more people who do stuff with programming, be able to utilize real physical phenomena in their work, whether they're creating video games or animations or something entirely unrelated. These concepts just involve some math, but it would be pretty awesome to see, like, I don't know, Command and Conquer mixed with Kerbal Space Program. If anybody could make that happen, let me know. That would be badass. If you found this video to be informative, please like and subscribe. Thanks, and have a good day.